Good afternoon, everyone. My name is Mayor Malfara, and I'm the Deputy Executive Director for the Electrical Association of Philadelphia. This afternoon, I am joined with my colleague, Matt Dybert, as well as our presenters and sponsor. I would like to welcome Chris Cleary, Marianne O'Connor with Staco Energy Products, as well as Scott Stiley with eSight Systems. Before we get started, please note that because we are recording today's session, your cameras and mics have both been turned off. You are welcome and encouraged to ask questions using the chat feature. They will be answered toward the end of the presentation. Now I'd like to turn it over to Scott. Scott?
Thank you, Mayor. Hello, everyone. Thank you for joining. Thank you for taking your time today to see this presentation. Again, I'm Scott Stilley from eSight Systems. We're a traditional manufacturer's rep. Along with the exciting Staco products that I have, I also have Thompson Power Systems, which is switchgear, paralleling gear, and ATSs, Mosbach load banks, flywheel systems, and motor gens, and then some products that go into data centers and mission critical sites is ABB, their static switches, PDUs, and etc. My territory is Eastern Pennsylvania, Southern New Jersey, and all of Delaware for Staco. I'm going to turn it over to Marianne. Marianne is my regional manager, and she's going to then introduce Chris Cleary. Take it away, Marianne.
Thanks a lot, Scott, and welcome everybody. Glad that you showed up, and we appreciate it. So about 4 months ago, Staco did a virtual talk for EAP on power factor, harmonics, UPSs, lighting inverters, and we want to continue that conversation and address more power quality and voltage regulation challenges and questions that we're all seeing in the field. And over its 85 years, and Matt, you can actually progress to so thank you. So over the past 85 years, Staco has really focused on power quality and voltage regulation applications and solving customer problems. And what's really great about Staco is they're very nimble, and our engineers love to solve problems and work with people, and finding solutions to help people with their issues. Which is another reason why we're probably seeing a great increase in containerized solutions as well with what we're offering. So some of the products that we had talked about were lighting inverters, power conditioners, harmonic filters, power factor corrections. So anything to do with power quality and voltage regulation. So in the effort to continue that conversation, I would like to introduce Chris Cleary, who will continue on and talk about more solutions and challenges we're seeing in the field and how we can address those. So thank you, and thank you, Chris.
All right. Well, hey, next slide, please. Okay, so when was the last time that power problems disrupted your day? Come on, we've all had them, right? We've had some type of, lights flicker, your computer flickers, something happens at work or at home or somewhere in between, and somehow your power is affected. So some type of a voltage fluctuation. Okay, that's what we'll be talking about today is voltage fluctuations, not only for testing products, but also for regulation to keep it a good steady voltage coming into, say, your equipment, your factory, your house, etc. A good example of this was a customer of ours that in Tulsa, Oklahoma, a customer had a sheet metal material handling system that was operating poorly. It was blowing circuit breakers. It was premature failures of electronic components. Customer could not figure out why, and what was happening was obviously the downtime with this material handling system. It was their sheet metal. It would feed their sheet metal processing equipment. No sheet metal is being fed. They can't do the processing and the work. So They actually ended up doing a power quality study and come to find out, since they were in an industrial park, that there was fluctuations throughout the day of the voltage, and their sheet metal material handling system was sensitive to those fluctuations. Could have been, plus or minus 10% or something to that effect. And what was happening was their electronic components were experiencing too much stress, and as a result, were failing early. We put a voltage regulator onto the material handling system, and the problem was solved. So sometimes what looks like what the problem might be, it might be somewhere else within your plant or within your house or within your machining center or operating area. Next slide, please. So the biggest concern is, how do your products react or respond to fluctuating voltage? Are they functionally tested, and are they fully protected? In the lower left-hand corner there, you'll see a lightning strike. That's the ultimate example of a voltage transient. Obviously that causes all sorts of problems, but that's just an extreme example of something that could happen in your factory or in your house. They're much more subtle than that. Somebody's turning on a motor, somebody's turning on a piece of equipment, starting up a computer, turning on the coffee machine, something like that could cause a transient. In the center there, you have microscopes. Those are very sensitive to voltage fluctuations, need to have good steady input power, so when that lab technician is looking at what's going on in that petri dish, she can be confident that she's looking at the right processes and making the right decisions from that. And then finally, we all have them. We all have dishwashers in our house, and they have yellow labels that come on. Those yellow labels don't just put themselves on there. Somebody has to put them on there. So the opposite side of the spectrum is to apply fluctuating voltage to the dishwasher to see what it does and how it performs. How much does it draw more current? Does the water pump not work as well? Does the rotating arm in the bottom of the dishwasher, does that not work, etc. So again, a couple different things that we want to talk about here. Next slide, please. And as Mary Ann was referring to, Staco Energy Products, one of the things that we do, we have catalog items. You want to call in and say, hey, I'd like to buy catalog item, 5011 BCT-3, you can certainly do that. But we specialize and have extensive experience in customization. On the left-hand side there, you'll see something we'll talk about a little bit later in detail. That's a fully customized solution where a customer came to us and said, hey, we need this to operate in all these different environments. Can you help us? And on the right-hand side, that array of variable transformers is a test set for an air conditioner manufacturer who needed to certify his equipment would operate in particular environments. Next slide. So, voltage control products, you say, what are they? In its most simplistic form, we have variable voltage transformers that have an input voltage, one input voltage, one output voltage. That output voltage is boosted 17% above the input voltage. So handy in terms of doing testing on particular product. We also have voltage regulators, which are a UPS without batteries. And what the voltage regulators do is they actually produce a very clean output signal so that you can have nice, steady power going into, say, your laser machining center. So both are voltage control products, but they control the voltage rather, in different ways. Next slide, please. So variable voltage transformers are, again, as I said, very simple in terms of how they have your input is one input and one output. It could be a three-phase input, it could be a single-phase input, and then it's got a widely varying output. The benefit of the widely varying output is that you can test products like pumps, you can test products like motors, like compressors, items like that to see what their performance is as the voltage varies. How much does the current increase when the voltage goes down? How much does it decrease? What size circuit breakers might be needed, etc. So we would put the varying output voltage into the item under test to see what its behavior is. Next slide, please. So then you've got applications. A couple of different applications that we'd like to talk about would be, for example, residential air conditioners. Central air conditioners are made by a variety of manufacturers. And one of the things that they have to do, again, is put that yellow sticker on there to say how efficient each model is. And they do that. The units are put into an environmental chamber where the temperature goes from minus 40 degrees to 140 degrees. There's humidity, there's snow, there's cold, there's all sorts of varying different conditions. And then the power is varied at the same time to see what the behavior of the air conditioner is, so they can certify it to be used in any environment. I have an air conditioner at my house that was actually tested by my product. So very confident in how it will perform. You also have applications for appliances. In that picture on the right-hand side, you can see there's a stove, there's a refrigerator, there's a microwave oven. All of those can be tested by our product with the variable voltage transformers. Again, steady input voltage to our variable voltage transformer. The transformer simply transforms the voltage into 117% of what the input was, so you can see what the behavior of the units of the item under test is. And it could be good, it could be bad, depending. But again, engineers want to get data. Production and quality people want to get the data on how the product is performing on their lines before it goes out into the field. We also have customers who are involved with, UL 508 panels, where they're going to have to test the various different circuits that are within there. Is there some type of a circuit breaker? What does the circuit breaker do? You subject it to, say, 15 volts and 3,000 amps, and see what the circuit breaker would do in terms of its performance, so that you can actually be confident when it's moved into the field and put into a UL 508 panel. Next slide, please. So this is where we come with active audience participation here. We've got a question for you. What is your familiarity with variable transformers? Is it extensive? You use them all the time? Is it moderate? You've seen it here or there. Maybe you worked at one place that had a lot. Now you're at a different place that does not. You've heard the term once or twice, or you're watching this wondering, what is a variable transformer? So take a few minutes and vote there.
We'll keep the poll open for 10 more seconds, and then we'll close it out and see what the results are.
All right, great. So terrific. So this is good. Then thank you very much for answering, and we'll try to provide as much information as possible based on those responses about variable transformers. So next slide, please. So a variable transformer, again, on the left-hand side there, you'll see our variable transformers with the gold plating. There's 3 of them stacked on top of each other with a motor that turns a wiper, people call it a wiper or a brush, turns that to go from 0 volts to whatever the full voltage happens to be. In this particular application, that'll be a 480 volt input, and the output would be 0 to 560, so 17% in boost. And it could be 5 or 15 or 30 seconds, possibly even 60 seconds to go around the actual variable transformer itself. Stacking them together like that, I know that that's a 3-phase unit, and that particular coil is what we call it, is rated at 35 amps. 35 amps per phase, And it could be any type of an application. That's the beauty of our units. They're very flexible in their application. They could be some other ones that I've just thought of would be, say, temperature control or lighting control or laboratory equipment testing, et cetera. We have benchtop models that are used in university fume hoods all the time. Then we've got a little bit more of an advanced look there on the right-hand side is what looks like a keypad and a screen. That is our microprocessor controller that allows for communication directly to the unit itself. So you can program in an output voltage via the keypad, or you can actually use serial communication capability and have that unit adjust the output voltage via, say, a PLC or an HMI or something to that effect, a computer, anything like that in terms of how you want to do it. And then that output will be regulated so that you can precisely test your units to a plus or minus 1 volt, possibly even better than that. So again, they're really kind of simple units. You have one input voltage and then a varying output voltage. Next slide, please. Okay, so our coils are actually manufactured in our Ohio facility. I invite everybody who's watching to come by and visit. We actually have engineering staff here. We have manufacturing and production staff here. We actually produce the coils right here in the factory that you can observe. From small ones that are in that middle photograph, you can see the hands that are surrounding them for reference points. Those are about 3 or 4 inches in diameter and weigh about 3 or 4 pounds. The one immediately to the right of that is a rather large coil that's rated at 35 amps, and it weighs about 50 pounds. But again, same function these units have, in that they have they're varying the voltage, a steady input, one input, and a varied output. Next slide, please. So now from there, we've learned that we can actually enhance the performance of our variable transformers by combining them in a couple of different unique ways. And that's where our test equipment comes in. Our test equipment allows total customization of the operation of the unit. Say, for example, I'm thinking of if there's multiple inputs. Maybe there's one or more than one input. Maybe there's more than one output. Perhaps you're doing a different frequency. Instead of 60 hertz, you have to do 50 hertz. Perhaps there's contactors in there, et cetera. So again, a little bit more complicated than just the simple in and one out of the variable transformers. Next slide, please. So this allows you to have many more applications that can be used. I mentioned HVAC industry. A lot of the HVAC industry is interested in 3 particular voltages: 240, 480, and 600. And they might be plus or minus 10% about that voltage itself. So they'd possibly be putting in, say, contactors with a tap and combine that with a tapped auto. What happens is the simplistic solution of the variable transformer, when you load the variable transformer, it loses, when you go to full load, it could lose up to 7 volts on its output side. So you're thinking you're getting 117%. You could possibly be getting 7 volts less than that. And what that means, maybe your motors don't start, maybe your compressors don't start, your dishwasher doesn't turn on, you cannot do the testing that you need to. So we can custom specify where the tap could be. We could get a 120% boost. However, you lose the current rating. As you go up in your boost and change this very specific location of where a tap is on the variable transformer, you lose your current rating. So, you know, a little bit here and there, so that again, you might have to add more variable transformers, increasing the cost of the system. So you've got to balance that economics with the design of the system. So for example, you'd add in a buck boost transformer. The buck boost transformer gets you the voltage that would stay steady when you would apply the full load. So a little bit more of a compact solution, a little bit more expensive. And then we would go from there. Looking at this picture right now, we've got that central picture with the unit that looks like a big gray industrial box. That unit is actually used to test electric vehicle charging stations, which are very popular now, appearing in a lot of company parking lots, a lot of retail location parking lots, etc. So that allows the electrical vehicle charging station to be tested, over the range of voltage, the range of current draw, etc. You could not do that with just a simple variable transform. You'd have to add some type of boosting capability, stabilizing capability of the voltage. Then that small picture at the bottom is a huge unit for a 2,000 amp air conditioner that's either a rooftop air conditioner or one of those ones that sits on the ground outside of the building. If you go to the next slide, please. In detail, you can see a number of different things going on. This is a three-phase system. So each phase is 2,000 amps. There are variable transformers in the background. You can see stacks and stacks of variable transformers. I believe that this particular unit has 54 of them. I could be corrected. I stand corrected on that. It could be 54. It might be a little bit less, but I'm pretty sure that it's 54 of those units. We've got a custom bus bar frame because there's so much current on there that we couldn't use the cables. The cables would be like using copper rods, so they'd be very difficult for people to work with. And the engineers designed bus bars based on the 2,000 amp capability. Plus, we've got a tapped auto and a tapped auto transformer in the front part of that picture right there. So that's a very creative, very customized solution. I cannot overemphasize enough how much creativity is involved with providing a solution for something like that. The customer simply asked us, hey, I need to test my 2,000 amp air conditioning unit, and I need to have steady voltage into it within this particular range. Our engineers came up with this economical solution that balanced variable transformers, buck boost transformers, tapped auto, the bus bars versus using copper wire, etc. All sorts of creativity to go into there to hit the economics of the scale, plus to actually hit the performance criteria that the customer needed. That to me is about the most creative as you can be as an electrical engineer. Other stuff, say electric vehicles, those are very, very high tech, very much out there. But there's creativity involved there. There's a lot of creativity involved with just simple transformers. Next slide, please. Oh yes, here we have some eye candy for everybody. Photographic evidence that indeed sales guys do actually go out in the field and do perform work when we're out there. That's a photo of me visiting a customer who is a manufacturer of what you and I would call a dishwasher, but what he calls a warewasher. If you can imagine, you're at a prison, you're at a hospital, you're at a university, you're at a large manufacturing facility that has, say, its own cafeteria, something like that, and you've got to wash all sorts of different things. You don't know if it's going to be silverware, you don't know if it's going to be cookware, you don't know if it's going to be glassware, the plates, etc. In any case, you've got to get those things in there, you've got to wash them, sterilize them, dry them, and get them back out again so that people can use them. That's why they call it a warewasher, because you never know what's exactly going to be in there. Plus, there's pumps and motors that are in there that need to be tested. They've got to certify these to certain standards of operation. So right beneath that photo, you can see, again, another gray box. This one has meters on the outside and even an old-fashioned analog meter. Yes, that's recently been upgraded, but for our purposes today, that's an analog meter. Where it's displaying the output voltage per phase. So this particular customer can set his voltage, can see what the voltage is per phase, can make individual adjustments should that voltage be imbalanced, and can test his wear washers of varying different sizes with our equipment. To the upper right there in the blue box is a motor testing system. We have a customer who makes all sorts of different motors, from little tiny ones that would go, say, in a hairdryer, to giant ones that would be used in any number of different places, most likely with pumps or something to that effect. And he needed a way to test those motors, and our system did that. That unit is rated for, I think it's 250 amps per phase, so a fairly large unit, considering the size of the motors. Excuse me. The final gray box that we have there is a 2,000 amp unit for a air conditioner manufacturer over in Virginia. He's using that to test his products. He's also got an array of push buttons on there that show he changes the frequency, and he changes what tap it's on, whether it's a 240 volt, 480, or 600 volt tap, so that he can actually see, test different units on this one piece of equipment. So next slide, please. Okay, so we've been talking about voltage fluctuation, where actually you induce the voltage fluctuation, meaning that you're operating a test. Here we have a voltage regulator that is exactly the opposite of that, where it takes a widely varying voltage and cleans it up, steadies it out, and makes it very stable on the output side. We got 3 different flavors for that. One would be the gray boxes that are called voltage regulators. Those are made here in our factory, and can go up to approximately, I believe, 1,500 kVA, so fairly big units. And they would be used in a variety of different applications, you know, for voltage swings, to make sure that you know, voltage was steady going into a machining center, for example, or a punch press, or you know, a wing of a factory or an office building or something to that effect. In the middle, we have our digital voltage regulators. Despite the fact they look like they're the same size as the previous versions, these are gigantic units that can go up to 5 MVA or 5,000 kVA, depending on your preference. And oftentimes their applications are very popular for these things are with wastewater treatment plants, where you're actually putting a voltage regulator on the inlet pumps, which you certainly don't want to have turn off, and have those continually operate with a steady voltage, so that the wastewater treatment can work its magic. And then on the right-hand side is one of our black boxes, which is a precision power conditioner, also known as a UPS without batteries. An uninterruptible power supply without batteries. So it will give you precise voltage regulation. It'll give you also known as power conditioning. Those terms are used interchangeably. Power conditioner, voltage regulator, you might have heard voltage stabilizer, etc. Next slide, please. And here's where we talk about Cleary's equation, one I invented myself, because it always kind of, when I was in grad school, I always wanted to have an equation or some type of formula or law named after myself, you know, I mean, a Fourier transform or Boyle's law, something, right? I had to come up with something. So we've come up with the Cleary equation, which shows that a PPS, or a piece of test equipment, is the inverse of a voltage regulator, and vice versa. So the test equipment takes steady voltage, makes it widely varying, right? The voltage regulator takes it exactly the opposite. Widely varying voltage makes it very steady. Different applications, but the same type of equipment on the inside. Variable voltage transformers, buck boost transformers, perhaps a tapped auto transformer. Next question. Next slide, sorry. So this here is our second question of the day for audience participation. Where do you think the majority of power problems come from? outside the facility, inside the facility, or somewhere completely different.
We got the poll up. We'll keep it open for about 15 seconds, and then we will share the results with Chris.
All right, look at that. Well, hey, I'll give you the answer in just a few minutes. But the audience is on to something. If we go to the next slide, which shows the causes of power problems from outside the facility, we've got all sorts of environmental problems. You've got weather, you've got lightning, you've got animals that like to that like to eat wires, that like to sit on the wires and do all sorts, things like that. You've got trees that fall down on production on power lines. You've got transmission line towers that possibly are not maintained, and they may fall over or be damaged in say a windstorm or something like that. You also have other issues such as that affect the grid reliability or the delivery of the power to your facility. There's a aging transmission system. There's, I believe, 4 energy grids in the United States, and all of them have to be at least probably older than I am, which is pretty old. But you've got demand situations where a place like in California, where they have rolling blackouts or rolling brownouts during the summertime because the demand is so high and they've got such a high population there. You've got personnel issues where maintenance workers are retiring and there's nobody coming in to replace them. So a labor shortage, and what that translates into is a reduction in maintenance of the items in the field. You've got, other things, consolidations and mergers and things like that affect the delivery of the power to the system, and also how the power is, what kind of power is being delivered from outside your facility. Next slide. And then you've got, your power problems inside the facility. You've got equipment failures. You've got an aging building. You can see on the left-hand side there with that terminal strip that it's overloaded. You've got maybe, one plug in an office building, and everybody, they put a terminal strip on there, and suddenly everybody's computer is hitched up to it. You've got, big copy machines now that require their own receptacle, but you don't have one available, so you just plug it into the most available one. You've got old buildings that don't have proper, up-to-date modern wires. That was a situation for Staco. The facility we were in up until 4 years ago was from 1940. It was very old. The wiring was old. The plumbing was old. All sorts of items were old within the building that did not contribute to modern Ethernet, modern communication methods, etc. And then, of course, you've got other things where there's new equipment that's used differently. You've got overloaded circuits. You've got something like that that's happening within the facility. So the winner is, inside your facility, roughly 70% of the power problems come from inside your facility. About 30% come from outside your facility. So next slide, please. Couple of the more popular types of power problems are a surge. You could have some type of a surge or an overvoltage. So in other words, and this surge could be caused by what? It could be caused by people turning their computers off, or people turning their welding machines off, or people go home at the end of the day and entire office building turns off their computer. Meanwhile, the production workers who are on second shift just experienced a voltage increase, and you've got to control that. You've got sags or under voltage, where, again, the opposite thing. 8 o'clock in the morning, people report to their desks, they turn on their coffee pots, they turn on their computers, they start doing a number of different things. So that brings the voltage down, and you've got to offset that and bring it back up to nominal levels. You've got transients that we've mentioned before, people turning on motors. people turning on welding equipment, people turning on banks of lights, et cetera, that come on and then just cause problems to come across your input voltage. Then one of my favorites, this is an actual picture I took of a vehicle in Mexico loaded with PVC pipe that was, as you can see, very unbalanced. But that's also an issue within your facility. If you've got three-phase power, one of those phases may be loaded excessively with single-phase loads. If that's the case, now you've got voltage imbalance, and you've got one phase that's lower or higher than another, and how's that going to affect how your units are operating? Next slide, please. Okay, so hey, we've got to talk about a couple of applications that are very interesting applications. Once we get done with these applications, we'll have a Q&A session and then wrap it up from there. But this first application is for, as you can see, the M1A1 tank trainer simulator. They needed steady voltage in the control areas so they could make sure that the tanks were able to operate properly. So steady voltage in the controls, I believe there was 9 trucks per site, and each one of those trucks had our voltage regulator located in the belly of the vehicle. So it was shielded from the elements, but again, it was still subjected to temperature fluctuations, and it worked to keep the controls up and running and steady so that they could properly train our tank operators. Very important. Next slide, please. In addition, I've been kind of bashing utilities, and justifiably so. But sometimes the utility substations need their own regulated power for the controls. As they're distributing the power, they need to have the controls be obviously up and running, and from those they need a steady input power. Our voltage regulators feed steady input power to the controls room, so that then when we as customers and consumers receive our power from, say, Duke Energy or Packlight or something like that, ComEd, that it's good steady voltage. Next slide, please. Last and certainly not least, one of my favorite applications. This is a custom application for an X-ray system. Inside of that shiny metal box is one of our precision power conditioners, a very fast-acting voltage regulator, so takes care of voltage problems instantaneously, and it's backing up an X-ray system that is inspecting trucks coming into the United States from Mexico and among other places. Most of them are deployed along the U.S.-Mexico border, but there are other deployments across around the world. And what they're, obviously you don't want that X-ray system to go down right in the middle of when a scan is being performed. So our units are completely self-contained. They're heated so that when it's less than 50 degrees, the electronics stay warm. When it gets at 50 degrees, the heater turns off, and then you've got an air conditioner that turns on around 95 degrees to keep the electronics cool. And not only is that used to see what's coming in over the border, another customer of that is the U.S. Mint, or the Bureau of Engraving in Fort Worth, Texas, where they don't really care what you bring in. They're worried about what you're taking out of that facility. So that's about it. That about wraps up our talking about the impact of fluctuating voltage on you and your products, from a couple different perspectives. Now we'd like to open it up for some Q&A.
Hey, thanks, Chris. Just a reminder, if there's any additional questions, feel free to put them into the chat. So one question, Chris, what or who is Staco's competition in this space?
Oh, great. That's a great question. We have one of our major competitors is to do nothing. Sometimes the equipment is a little bit more expensive than what people anticipated it to be. And so to do nothing is some of our competition. There's also electronic test equipment that performs the same type of activities. They have a little bit more flexibility, but they're a little bit more expensive. They don't have the same level of durability or ability to take heavy overload as our units do. Our variable transformers are very immune to high overload, whereas the electronic units, a growing competitor, are not quite as immune to that. IGBTs are sometimes sensitive to overload.
Thanks, Chris. In the chat, do you cover UE voltages and have subsidiaries overseas?
We do cover any voltage and any frequency. We do have representatives overseas in UAE, for example. We do have representatives. We have put applications in India. So we would be able to handle any type of voltages for overseas applications from a voltage aspect, current aspect, and a frequency aspect.
Thanks, Chris. Kind of a follow-up to that. What is your size range in terms of volts and amps?
Ooh, okay. So we've had applications that can go up to 1,500 volts, and other applications that have gone up to 3,000 amps. So we can do pretty much anything. Our sweet spot most of our applications are 0 to 700 volts, and probably around 100 to 250 amps. But again, we can go up to 1,500 volts and up to 3,000 amps.
Thanks, Chris. Another one. What are the typical lead times on your equipment?
Typical lead times. Always a very flexible number, but our typical lead time, if we're looking at a custom piece of equipment, is somewhere in the 12 to 16 week range. From the design aspect, because we consult with the customer, we come up with we agree to what the unit should look like, so we sign off on the drawings together, and then we put the unit into production. And that process takes, somewhere around the order of 12 to 16 weeks.
Thank you, Chris. Do your units have internal bypasses in the event of an internal failure?
On the test equipment, no, we do not have that. Our voltage regulators typically do not have a bypass in them. You would just switch over to utility voltage at that point in time.
Thank you. Let's see here. Some more questions. What are automation options you may have?
Automation options. We have the what we call the microprocessor 2 controller that allows you to have serial communication, RS-232, RS-485, remote analog controls, 4 to 20 milliamps. Our precision power conditioners have a full-on screen there for communication for a variety of levels, up to and including sending a text message if there's an error in the unit. So between the microprocessor controller for the test equipment and then the panel for our precision power conditioners, we have a couple of different options.
Great. Let's see. One more. What do you have that is new or in development?
One of the things that we have is as I mentioned, the MP2 controller. We are looking at engineering is actively updating that to a more modern configuration, including flat screen display, an adjustable display so that you can put various different software modules on it, different types of communication where we're looking at possibly Ethernet and Modbus. So developing a more advanced microprocessor controller for our test equipment, because a lot of customers are using software such as LabVIEW, or they're very interested in what the data would come up with for the tests that they're running.
Great. So thank you for all the questions in the chat. I don't see anything else. So,
Okay, together we will power on. Okay, I want to thank Chris, Marianne, and Scott for a great presentation. We will be emailing everyone with the speaker's contact information. The recording will be posted on EAP TV at www.eap.org/TV early next week. I would like to thank everyone for joining us today and have a great day. Take care.